Hello and welcome to the Math Studio. In this video, we're going to have a brief discussion on the limit definition of the derivative. And it's actually based upon this fundamental problem here. What is the gradient of the tangent to the curve y equals function x at point P? So here's our diagram, here's our y equals function x. Okay, so it's just an arbitrary function, doesn't resemble anything necessarily. Okay, here's our point P. Okay, and it's got coordinates x comma f of x, and that sits on the curve. Our red line here represents our tangent, so that touches the curve at just one point, obviously at point P. Now our blue line here is secant AP, and I'll talk about that shortly. So back to our fundamental problem. We want the gradient of the tangent, but we only have one known point. In order to be able to work out the gradient of a line, we need 2 points, don't we? So this is our y2 minus y1 over x2 minus x1. So it's sort of our 2-point gradient formula. Okay, but what do we do about this? We've only got 1 point. So in order to be able to at least come up with an estimate of the gradient of the tangent at P, we need to use a second point somewhere. So let's say we chose another point. So let's say we chose point A, a little bit further along on the curve. Now point A is a little bit further along than point P in terms of horizontally. So if point P has an x coordinate of x, we're going to move h units along. Point A will have an x coordinate of x plus h, so h units sort of along. The y coordinate of point A will be f of x plus h. So in other words, substituting x plus h into whatever function we have, that'll give us our y value. Now we have 2 points. We can at least estimate the gradient of the tangent at point P by just using this point A and point P and using the 2-point formula for gradient. So the gradient of the tangent at P is approximately equal to the gradient of secant AP, provided we chose point A not too far away from point P, of course. Now, I'm going to write this using the proper notation. F dash of x, that just represents our tangent, or the gradient of our tangent. This red line here. So this is f dash or f prime. So f dash of x is approximately equal to f of x plus h minus f of x over x plus h minus x. So that's y2 minus y1 over x2 minus x1. Now, of course, the x plus h minus x, the x's cancel. Okay, so we can cross those off. And we end up with f dash of x is approximately equal to f of x plus h minus f of x over h. Now, how do we make the estimate of the gradient of the tangent at point P more accurate? And it's pretty clear that we need to move point A closer and closer to point P. So how do we achieve that? Remember that point A is h units away from point P, at least horizontally. So if we make h smaller, in other words, we're bringing point A closer and closer to point P, the blue line, at least the gradient of the blue line, begins to approach the gradient of the red line, the tangent. So, and I've written this here. So now the gradient of secant AP approaches the gradient of the tangent at P as h approaches 0. Okay, we have another fundamental issue that now comes up. What happens if you make h 0 here? Well, you've got a run of 0, and that creates a problem in itself. You can't have division by 0. So therefore we have this operator, this limit operator, that'll sort of help us in this process. Now, if we can somehow make h 0, then the secant, or the gradient of the secant, equals the gradient of the tangent. That's no longer an estimate. So f dash of x is in fact equal to, no longer approximately equal to, but equal to the limit. So think of the limit as like an endpoint, sort of an end value. The limit as h approaches 0 of f of x plus h minus f of x, so that's our rise, so y2 minus y1, over our run of h. In subsequent videos, I will look at examples of this, so thank you very much for watching and wishing you all the best for your studies. Hello and welcome to the Math Studio. In this video, we're going to look at a simple example of differentiation by first principles. Differentiate by first principles the function y equals x squared. So let's start off with the definition. So that's y dash, or our first derivative, is equal to the limit as h approaches 0, f of x plus h minus f of x over h. So a good way to sort of think about this is it's really rise over run. Okay, so difference in the y values, and h represents the difference in the x values. So f of x plus h, if we substitute x plus h into the original function, so replace the x with x plus h and then square it, you get x plus h all squared minus x squared over h. Okay, so that's the limit as h approaches 0 of what's in the brackets there. Now if we expand the x plus h squared, we get y dash is equal to the limit as h approaches 0, x squared plus 2xh plus h squared minus x squared, so that's our f of x over h. And the x squareds, in fact, cancel, so you got x squared minus x squared, so they cancel to 0. And we get y dash is equal to the limit as h approaches 0 of 2xh plus h squared over h. Now, factorizing out the h in the numerator, we get y dash is equal to the limit as h approaches 0, h outside of 2x plus h over h, and of course, the h's will cancel, and I might just indicate that now, so they disappear. And we end up with y dash is equal to the limit as h approaches 0 of 2x plus h. Now that there's no more denominator, or at least the denominator of h has disappeared and effectively become sort of a 1, we can now apply the limit by letting h equal 0. So y dash is equal to 2x plus 0, so that's where our h was, and it's been replaced now with h equals 0, so, well, 0 we don't have to show. Therefore, y dash is equal to 2x. Hello and welcome to the Math Studio. In this video, we're going to look at another example of differentiation by first principles. So differentiate by first principles the function y equals x cubed. So the limit definition is stated as y dash, so the first derivative is equal to the limit as x approaches c of f of x minus f of c over x minus c. So again, this is like our rise over run. So this is similar to the f of x plus h definition, as you know, where h approaches 0. This one, x is approaching c. So again, the 2 points are being brought closer together by letting x get closer and closer to point c. And this is also like your y2 minus y1 over x2 minus x1. So the next line would read y dash is equal to the limit as x approaches c, and replacing the f of x with the actual function itself, which is x cubed, and f of c, so replacing the x with c, we get c cubed. So x cubed minus c cubed over x minus c. And if you factorize the numerator, we get y dash is equal to the limit as x approaches c of x minus c outside of x squared plus xc plus c squared. So this is the factorization of a difference of 2 cubes. So x cubed minus c cubed, difference of 2 cubes over x minus c. And of course, you'll probably notice that the factor x minus c cancels with the denominator x minus c. And that's very nice because that's what we want, or else you'll have a division by 0 when you apply the limit. So that gives us y dash is equal to the limit as x approaches c of x squared plus xc plus c squared. Now at this point, we don't have any nasty denominators that are going to equal 0, so you end up with a division by 0. So now we can apply the limit by letting x equal c. So y dash is equal to c squared. So basically wherever you see an x, replace it with a c. So c squared plus c times c plus c squared. And that gives us y dash is equal to c squared plus c squared plus c squared. And that gives us y dash is equal to 3c squared when you collect the like terms. But we know that x equals c, and therefore c equals x. So we can replace the c with the letter x, because we want the derivative in terms of x, of course. So y dash is equal to 3x squared. Thank you for watching. Hello and welcome to the Math Studio. In this video, we're going to look at differentiating the function y equals the square root of x by first principles. And to save some time, I've pre-written the proof, but I'm going to go through that with you to assist your understanding. Now, this proof is based on the alternative limit definition of the derivative, which is y dash equals the limit as x approaches c of f of x minus f of c over x minus c. Okay, so our first step is going to be, let's just substitute the f of x and f of c with the actual function, the function itself. So y dash is equal to the limit as x approaches c. Now f of x is replaced with the square root of x, because that's what f of x is. And f of c is just the square root of c. So we're just replacing the x with c over x minus c. Now we have a problem here in that if we apply the limit now, and you let x equal c, you're going to have a division by 0. So we're going to deal with that by rationalizing the numerator, strangely enough. I know usually we rationalize the denominator, but in this case, we're going to rationalize the numerator. And we're going to do that by multiplying the numerator and the denominator by the conjugate of the numerator, which is square root of x plus the square root of c. But you've got to sort of do the same thing top and bottom, of course. So when you multiply the numerator, you've got to also multiply the denominator by the same factor. So now notice that you have a difference of 2 squares in the numerator there. So that's sort of a nice consequence of multiplying by the conjugate. It'll rationalize the numerator. So what you end up with here then is y dash equals the limit as x approaches c of x minus c over x minus c multiplied by the square root of x plus c. Now you'll sort of have a nice thing occurring here, which is the numerator will cancel with the factor x minus c in the denominator, and then you end up with y dash equals the limit as x approaches c 1 over square root of x plus the square root of c. So what's nice about this is that you will not get a division by 0 if you apply the limit. So I think it's safe now that we can apply the limit. So now apply the limit by letting x equal c, or we can let c equal x. Either way, we're letting the x and the c being sort of equal to each other. So what I'm going to do is I'm going to replace the c with an x, and we end up with y dash equals 1 over the square root of x plus the square root of x. And of course, that we can sort of collect the like terms, and we end up with y dash, or the first derivative, is equal to 1 over 2 times the square root of x. And of course, you can differentiate this using a fast method, and of course, you'll end up with the same thing. But I think it's good to be able to see sort of how we arrive at this result by first principles. Thank you for watching. Differentiate the function y equals x to the power of 5 minus 3x squared plus 1. Now, the derivative of the function is found by differentiating the individual terms. So the derivative of x to the power of 5 is 5x to the power of 4. So the old power becomes the multiplying factor, and you also reduce the old power by 1. So 5 minus 1 is 4. Now, the derivative of negative 3x squared is done the same way. So the 2, the old power, becomes the multiplying factor. The 3 stays intact, and then the old power is reduced by 1, so 2 minus 1 is 1. And the derivative of a constant term, regardless of its value, is always 0. So just simplifying the algebra now, therefore, y dash, or the first derivative, is equal to 5x to the power of 4 minus 6x. Differentiate the function f of x equals 2x to the power of negative 4 plus x to the power of 2/3. Now, the rules of differentiation apply to negative indices as well as fractional indices. So f dash of x is equal to negative 4 times 2x to the power of negative 5. So the negative 4 becomes a multiplying factor, and the old power is reduced by 1. And the same thing for x to the power of 2/3. So the 2/3 becomes a multiplying factor, it comes out to the front, and the old power is reduced by 1. So therefore, f dash of x, or the first derivative, is equal to negative 8, x to the power of negative 5, plus 2/3, x to the power of negative 1/3. Differentiate y equals x plus 3 in brackets multiplied by 3x minus 1 in brackets. Now, this is a function that's a product of two binomials, so we can expand the brackets first and then differentiate the function according to the usual rules. So expanding the brackets, we have y equals 3x squared plus 8x minus 3, and then differentiating the function, we have y dash is equal to 6x plus 8. Find the gradient and the angle of inclination of the tangent to the curve f of x equals x squared plus 3x at the origin. Our first step is to differentiate the function. So f dash of x is equal to 2x plus 3. Our next step is to find the gradient of the tangent at the origin. That's when x equals 0. So f dash of 0 is equal to 2 times 0 plus 3, which is equal to 3. Our next step is to find the angle of inclination. So theta is equal to inverse tan of 3. So that's how we find the angle of inclination. 3 represents the gradient, and that equals 71 degrees and 34 minutes, correct to the nearest minute. Therefore, gradient of the tangent is 3, and its angle of inclination is 71 degrees and 34 minutes. Find the points on the curve f of x equals 2x cubed minus 15x squared plus 36x minus 1, where the gradient of the tangent is horizontal. Our first step is to differentiate our function to find the gradient function. So f dash of x is equal to 6x squared minus 30x plus 36. Our next step is to set our gradient function equal to 0 because we're interested in the points where the tangent is horizontal. So 6x squared minus 30x plus 36 is equal to 0. Dividing both sides by 6, so we have x squared minus 5x plus 6 equals 0. This is a monic quadratic, and we can solve that, of course, so therefore x equals 2 or 3. Now we need to find the y values that correspond to x equals 2 or 3, so f of 2 is equal to 27, that's going back to the original function to find that. F of 3 is equal to 26, so therefore the points on the curve where the tangent is horizontal are 2, 27 and 3, 26. Find the equation of the tangent to the curve y equals x squared plus 3x minus 1 at the point -4, 3. Our first step is to find the gradient function by differentiation. So y dash is equal to 2x plus 3. Our next step is to find the gradient of the tangent at this point. So we're going to substitute x equals -4 into the gradient function, and we have y dash is equal to -5. Our next step is to use the point gradient formula to find the equation of the tangent. So that's y minus y1 is equal to m outside of x minus x1. So our m is the gradient, so that's -5. Our y1 is the y coordinate, that's 3, and our x1 is -4. So substituting those three values in and just cleaning up the algebra and simplifying, we end up with y equals -5x minus 17. Find the equation of the normal to the curve f of x equals 1 minus x cubed at the point 2, -7. Our first step is to differentiate the function to find the gradient function. So f dash of x is equal to -3x squared. Our next step is to find the gradient of the tangent at the point where x equals 2. So f dash of 2 is equal to -3 times 2 squared, which is equal to -12. Our next step is to find the gradient of the normal. So that's the negative reciprocal of the gradient of the tangent. So that's -1 over -12, which is equal to 1 over 12. Our final step is to find the equation of the normal by applying the point gradient formula. So y minus -7 is equal to 1 on 12 outside of x minus 2. And simplifying the algebra and presenting the equation in general form, we have x minus 12y minus 86 equals 0 as the equation of the normal. Find the third derivative of the function y equals x squared plus 5x plus 1. Note the 4 different ways that we can denote the first derivative. So we have y dash, f dash of x, f to the 1 of x, but the 1 needs to be in brackets, and dy dx. And the first derivative is 2x plus 5, using our usual rules of differentiation. The second derivative is denoted by y double dash, or f double dash of x, or f2 of x, or d squared y over dx squared. And that's found by taking the derivative of the first derivative, and that's 2. And the third derivative is denoted likewise, as you can see, so y triple dash, or f triple dash of x, f3 of x, or d cubed y over dx cubed. And that's found by taking the derivative of the second derivative, and that's a constant, so that's 0. Find the family of curves with derivative dy dx equals 9x squared plus 4. In order to do that, we need to reverse the process of differentiation. So if by differentiating we multiply the term by the old power and then subtract 1 from the old power, reversing that, sometimes called anti-differentiation, we add 1 to the old power and then divide the term by the new power. So if dy dx is equal to 9x squared plus 4, starting off with the 2, we add 1 to it, becomes 3, and then we divide the entire term by 3. Then starting off with the 4, if it's just a constant and we anti-differentiate, you just add an x to the 4. Don't forget also we need to add a plus c, because the original function might have had a constant in it which disappears when you differentiate it. So therefore, y equals 3x cubed plus 4x plus c, where c is a constant. Find the family of curves with derivative y dash equals 15x to the power of 4 minus 12x squared plus 8. Now, because we're starting with the first derivative, we need to reverse the process of differentiation to get back to the original function and then to find this family of curves. So differentiating involves multiplying by the old power and then subtracting 1 from the old power. To reverse this process, we add 1 to the old power and then divide by the new power. So if y dash is equal to 15x to the power of 4 minus 12x squared plus 8, we add 1 to the powers, so the 4 becomes a 5 and the 2 becomes a 3, and then we divide by the new power. So y is equal to 15x to the power of 5 over 5 minus 12x cubed over 3 plus 8x, so a constant just has an x added to it. Therefore, y is equal to 3x to the power of 5 minus 4x cubed plus 8x plus c. Don't forget, we need to add the constant, so that's where c is a constant. And we can check our answer by differentiating it, and you should get back to y dash given in the original question. Find dy dx given y equals x cubed plus 1 all to the power of 6. Now this is a function of a function, so we're going to use the chain rule. Let u equal x cubed plus 1, so that's the inner function. Then y equals u to the power of 6, so x cubed plus 1 is concealed in the u. Then by the chain rule, dy dx is equal to dy du multiplied by du dx. Now dy du we find by differentiating this function here, this y equals u to the power of 6, and that's 6u to the power of 5. And du dx is found by differentiating this function here. So u is equal to x cubed plus 1, so therefore du dx is equal to 3x squared. So multiplying all that together, we end up with 18x squared, u to the power of 5, but we want the derivative in terms of x, so we substitute out the u, and in its place we substitute x cubed plus 1, so therefore dy dx is equal to 18x squared multiplied by x cubed plus 1 all to the power of 5. Find the derivative of 3 outside of 7 plus x minus 2x squared all to the power of 5. Now this is another example of a function of a function. So we're going to apply the chain rule. If y equals f of g of x, then y dash, the first derivative, is equal to f dash of g of x multiplied by g dash of x. So what this means is the derivative of the outer function multiplied by the derivative of the inner function. So y dash is equal to 15 outside of 7 plus x minus 2x squared all to the power of 4. So this 5 has come down to the front and the power is reduced by 1. But then we need to multiply it by the derivative of the inner function. So that's the derivative of 7 plus x minus 2x squared, which is 1 minus 4x. And then tidying up this expression, we have y dash is equal to 15 outside of 1 minus 4x outside of 7 plus x minus 2x squared all to the power of 4. Find the points on the curve y equals 1 minus x to the power of 4 all to the power of 3 where the tangent is horizontal. Now a horizontal tangent implies y dash, or the first derivative, is equal to 0. Now this is a function of a function or a composite function. Therefore we can use the chain rule to differentiate this. So differentiating the outer function multiplied by the derivative of the inner function. So y dash is equal to 3 outside of 1 minus x to the power of 4 all squared multiplied by negative 4x cubed. And that gives us negative 12x to the power of 3 multiplied by 1 minus x to the power of 4 all squared. Then we'll let that equal 0 and then solve for x, and we end up with x equals negative 1, 0, or 1. Now we use these x values in the original function then to find the corresponding y values. So therefore, the points where the tangent is horizontal are negative 1, 0, 0, 1, and 1, 0. Differentiate the function defined parametrically by x equals 3t and y equals 4t squared. Now because x and y are defined in terms of a third variable t, we can apply the chain rule. dy dx is equal to dy dt multiplied by dt dx. But we really want dx dt because x is in terms of t and not the other way around. So we can rearrange the chain rule so that it's dy dt divided by dx dt. So the multiplication symbol turns into a division symbol, and we just flip the dt dx so it becomes dx dt. Now dy dt is found by differentiating this function here, and that's 8t, and dx dt is found by differentiating this function here, and that's 3. And that's equal to 8t over 3. But t is equal to x over 3 if you rearrange x equals 3t and make t the subject. Therefore, dy dx is equal to 8x over 9 if you substitute x over 3 for t. Differentiate y equals the square root of x by forming the inverse function. So I'm going to start off by swapping the left and right hand sides of the equation around. So square root of x equals y. Now I'm going to make x the subject of the formula by squaring both sides. So x is equal to y squared. Now I'm going to use the property that dy dx is equal to 1 over dx dy. Now dx dy we can find easily because x now is in terms of y. So the derivative of y squared is 2y. So dy dx is equal to 1 over 2y. But we want the derivative with respect to x. Y is equal to the square root of x. That's by definition. Therefore, dy dx is equal to 1 over 2 square root of x. Find the derivative of 5x to the power of negative 3, giving the answer as a fraction. Now we can differentiate this function as if we were differentiating a function with a positive power. So the negative 3 comes out to the front and becomes a multiplying factor, and then we subtract 1 from negative 3. So dy dx is equal to negative 3 times 5x to the power of negative 4, which is equal to negative 15x to the power of negative 4. And now expressing it as a fraction, a negative index means it's a reciprocal, so therefore it can be expressed as dy dx is equal to negative 15 over x to the power of positive 4. Differentiate the function f of x equals 3 over 5x to the power of 4. So I'm going to start off by expressing the reciprocal using a negative index. So f of x is equal to 3 over 5 multiplied by x to the power of negative 4. Now we can differentiate it using the usual method. So f dash of x is equal to negative 4 times 3 on 5 times x to the power of negative 5. So the negative 4 comes out to the front and we reduce the power by 1, which is equal to negative 12 over 5 times x to the power of negative 5. And we can now express this as a fraction. So f dash of x is equal to negative 12 over 5x to the power of positive 5. Differentiate y equals 1 over 5 minus x to the power of 3. So first we're going to express the reciprocal using a negative index, and then we're going to apply the chain rule to differentiate it. So y is equal to 5 minus x cubed all to the power of negative 1. Now we're going to apply the chain rule. So we're going to differentiate the outer function and then multiply it by the derivative of the inner function. So y dash, first derivative, is equal to negative 1 multiplied by 5 minus x cubed all to the power of negative 2 multiplied by the derivative of the inner function, which is negative 3x squared. Now simplifying this product, we have y dash is equal to 3x squared multiplied by 5 minus x cubed all to the power of negative 2. Then expressing the derivative as a fraction, we have y dash is equal to 3x squared over 5 minus x cubed all squared. Differentiate the function y equals 5x cubed plus 2 all over x. So I'm going to express this fraction as a sum of two fractions, 5x cubed over x plus 2 over x. Now 5x cubed over x simplifies to 5x squared, and the reciprocal 2 over x may be expressed using a negative index as 2x to the power of negative 1. Now we can differentiate this function. So y dash is equal to 10x plus negative 1 times 2 times x to the power of negative 2, which is equal to 10x minus 2x to the power of negative 2, which is equal to 10x minus 2 over x squared. So that's expressing the negative index as a reciprocal with a positive index. And we can combine these two terms into a single fraction. Y dash, or the first derivative, is equal to 10x cubed minus 2 all over x squared. Differentiate y equals 10 times the square root of x. Now surds should be expressed using a fractional index before differentiating. So this function can be written as y equals 10 times x to the power of half. This can now be differentiated using the usual method. So y dash is equal to half times 10 times x to the power of negative half. This simplifies to y dash is equal to 5x to the power of negative half. We can now express this in fraction form since it's a negative index. So y dash equals 5 over x to the power of half. But x to the power of half represents a surd, so we can express this in surd form. So therefore, y dash is equal to 5 over the square root of x. Differentiate y equals 1 all over x cubed multiplied by the square root of x. Now this function involves a surd and a reciprocal, so we need to express this function using a negative fractional index. So y is equal to x cubed multiplied by x to the power of half, all to the power of negative 1. So x to the power of half represents the surd, and to the power of negative 1 represents the reciprocal. So y is equal to x to the power of negative 7 over 2. We can now differentiate this using the usual methods. So y dash is equal to negative 7 over 2 multiplied by x to the power of negative 9 over 2. So that subtracting 1 from negative 7 over 2, we get negative 9 over 2, which is negative 4.5. Now that's a negative index and a fractional index. So we can express this using a surd and in fraction form with a positive index. So y dash is equal to negative 7 all over 2 times x to the power of 4 times the square root of x. Differentiate y equals 1 over the square root of 1 plus 4x squared. Now this function involves a surd and a reciprocal, and it's also a composite function, so we need to express this function using a negative fractional index and then apply the chain rule. So y is equal to 1 plus 4x squared all to the power of negative half. We can then differentiate this using the chain rule. So the derivative of the outer function, so the negative half comes out to the front, and we reduce the negative half by 1, so it becomes negative 3 over 2. And then we multiply it by the derivative of the inner function. So the derivative of 1 plus 4x squared is 8x. This simplifies to y dash equals negative 4x multiplied by 1 plus 4x squared to the power of negative 3 over 2. And it's a negative index, so we can express this in fraction form. So therefore, y dash is equal to negative 4x all over 1 plus 4x squared to the power of 3 over 2. Differentiate y equals 12x plus 8 over the square root of x. We're going to express this as the sum of two fractions using fractional indices. So y equals 12x over the square root of x plus 8 over the square root of x. If we rationalize the denominator in the first fraction, we obtain y equals 12 multiplied by the square root of x plus 8 over the square root of x. Now expressing the surds using fractional indices, we have y equals 12 times x to the power of half plus 8 times x to the power of negative half. Now differentiating this function using the usual method, we have y dash is equal to 6 times x to the power of negative half minus 4 times x to the power of negative 3 over 2. So expressing these fractional indices in surd form and in fraction form, we have y dash, or our first derivative, is equal to 6 over the square root of x minus 4 over x root x, and this simplifies to y dash equals 6x minus 4 over x root x. The product rule of differentiation. Let y equal f of x multiplied by g of x, where f of x and g of x are functions in x. Then dy dx, so the derivative of this function there, is equal to f dash of x multiplied by g of x plus f of x multiplied by g dash of x. This is called the product rule of differentiation. Now there is an alternative way that we can express this rule, and we can use the yuv notation. So given y is equal to u multiplied by v, where u is equal to f of x and v is equal to g of x, then y dash is equal to u dash v plus uv dash. So u is just f of x, so there's your f dash of x represented by u dash there. And v dash represents g dash of x there. Let's have a look at an example. Find dy dx given y is equal to x squared outside of x plus 1 to the power of 5. Now, this binomial and its power is high enough that it's probably not feasible to expand this. I mean, you could, but you'd be there for a while. It's much quicker to use the product rule because we can see that this is really just the product of two functions. We have an x squared, that's a function, that can be our f of x or our u, and we have x plus 1 to the power of 5, and that's our v. In fact, I might just annotate it here. So that's our u, and this is our v. So if we let u equal to x squared, then u dash is equal to 2x, so we just differentiate the u. If we let v equal to x plus 1 to the power of 5, then v dash is equal to the derivative of this, obviously, which is 5 outside of x plus 1 to the power of 4. Then y dash, so the first derivative, is equal to u dash v plus uv dash, which is equal to 2x multiplied by x plus 1 to the power of 5. Sometimes I use something that resembles the cross method. So if you multiply those two together, that's your u dash v, then plus uv dash, so x squared multiplied by 5 outside of x plus 1 to the power of 4. So that way. And that is our first derivative. We could factorize this further if we wanted to. We could take out a common factor of x or take out a common factor of x plus 1 to the power of 4 and simplify it or factorize it further. But at this point, I'm just going to leave it as it is. Find the derivative of x squared multiplied by 3x plus 2 all to the power of 3, expressing your answer in fully factored form. Now we're going to apply the product rule here. So we're going to let y equal uv, where u is equal to x squared, and v is equal to 3x plus 2 all to the power of 3. Hence, u dash is equal to 2x, so the derivative of x squared, and v dash is equal to 9 outside of 3x plus 2 all squared. So this is accomplished using the chain rule. Now y dash is equal to u dash v plus uv dash, which is equal to 2x outside of 3x plus 2 all cubed, plus 9x squared outside of 3x plus 2 all squared, which is equal to x outside of 3x plus 2 all squared outside of 6x plus 4 plus 9x. So that's factorizing out the x and the 3x plus 2 all squared. And then adding the like terms in the last bracket there, we get y dash is equal to x outside of 3x plus 2 all squared outside of 15x plus 4. Find the gradient function of y equals x outside of the square root of x plus 1. Now gradient function means find the first derivative. Now y is a product of two functions, hence we apply the product rule. So we're going to let u equal x and v equal x plus 1 to the power of half. So converting the Surd form into fractional index form. Then u dash equals 1 and v dash equals half outside of x plus 1 to the power of negative half. So that's applying the chain rule. Now y dash is equal to u dash v plus uv dash. So that's from the product rule, which is equal to x plus 1 to the power of half. So there's our u dash v plus half multiplied by x plus 1 to the power of negative half. And that's our uv dash. So that's equal to the square root of x plus 1 over 2 the square root of x plus 1. And expressing these two terms with a common denominator, we get y dash is equal to 2x plus 3 over 2 outside of square root of x plus 1. Find the derivative of y equals uvw, where u, v, and w are functions of x. Now this will require multiple applications of the product rule. Let's start by grouping u and v together in brackets so it behaves like a single term. Y equals uv in brackets multiplied by w. Now let's apply the product rule. Y dash is equal to uv dash w plus uv w dash. So this is our first application of the product rule. But uv dash, so the derivative of this product, u times v, is equal to u dash v plus uv dash. So this is the second application of the product rule. Now putting it all together, we have y dash is equal to u dash v plus uv dash w plus uv w dash. Expanding the brackets, we have y dash is equal to u dash vw plus u v dash w plus uv w dash. The quotient rule. Let y equal f of x over g of x. Then dy dx, so first derivative, is equal to f dash of x times g of x minus f of x times g dash of x over the square of g of x. Alternatively, if you want to use yuv notation, if y is equal to u over v, where u and v are functions of x, then y dash, the first derivative, is equal to u dash v minus uv dash over v squared. Now the quotient rule is applied if the variable to differentiate, in this case x, well usually we use the pronumeral x, appears in both the numerator and the denominator. So for example, y equals 3 over x squared does not require the quotient rule because the variable x only appears in the denominator, not in the numerator as well. So it has to be in both. However, this example, y equals 3x squared over x plus 1, requires the quotient rule because the variable x appears in one way, shape or form. It appears in the numerator and the denominator. Hence, the quotient rule is required. Now let's have a look at an example. Find the derivative of 3x squared over x plus 1. So let's let the numerator be u and the denominator be v. So let u equal 3x squared, which means u dash is equal to 6x, so the derivative of 3x squared. Let v equal x plus 1, and the derivative of v dash is equal to 1. Now let's apply the quotient rule. So y dash is equal to u dash v minus uv dash over v squared. And that's equal to 6x times x plus 1 minus 3x squared times 1 over x plus 1 all squared. Okay, so you can see the u dash v there, so 6x times x plus 1 and minus 3x squared times 1. Okay. So if we simplify the algebra, so that equals 6x squared plus 6x minus 3x squared over x plus 1 all squared. And that simplifies to y dash, so first derivative is equal to 3x outside of x plus 2 all over x plus 1 all squared. So there's no need to expand the denominator. Usually we just express it in factorized form or in simplest form, and that's it. Find the points on the curve y equals x over x squared plus 1 where the tangent is horizontal. We're going to apply the quotient rule because the variable x appears in both the numerator and the denominator. So y dash is equal to u dash v minus uv dash over v squared. Let u equals x, so that's the numerator, therefore u dash equals 1. Let v equal x squared plus 1, so that's the denominator, therefore v dash is equal to 2x. Hence y dash is equal to x squared plus 1 minus 2x squared over x squared plus 1 all squared. And that simplifies to 1 minus x squared all over x squared plus 1 all squared. Now the tangent is horizontal when y dash is equal to 0, so the first derivative is equal to 0. And that occurs when the numerator is equal to 0. 1 minus x squared is equal to 0. So solving that, we have x equals -1 or 1. Now to find the y values that correspond to that, we need to substitute these values of x into the original function. Therefore, the tangent is horizontal at the points -1, -1/2 and 1 comma half. Find the gradient function of y equals square root of x plus 1 over square root of x minus 1. Now we're going to apply the quotient rule because the variable x appears in both the numerator and the denominator. So let u equal square root of x plus 1, u dash is equal to 1 over 2 square root of x, v is equal to square root of x minus 1, v dash is equal to 1 over 2 square root of x. Now y dash is equal to u dash v minus uv dash over v squared. Now to simplify this fraction, we're going to multiply every term by 2 square root of x to eliminate this denominator here. So that becomes y dash equals square root of x minus 1 minus the square root of x plus 1. So notice the brackets around the square root of x plus 1, so that's important, over 2 square root of x outside of square root of x minus 1 all squared, and that eventually simplifies to y dash equals negative 1 over square root of x outside of square root of x minus 1 all squared. Differentiate y equals x plus 1 over x plus 2. Option 1, we can use the quotient rule since the variable x appears in both the numerator and the denominator. Option 2, we can avoid using the quotient rule by rearranging the fraction and then differentiating using the usual method. I'm going to use option 2. Y equals x plus 1 over x plus 2 can be written as y equals x plus 2 minus 1 over x plus 2. This fraction can be split up such that y equals x plus 2 over x plus 2 minus 1 over x plus 2. This simplifies to y equals 1 minus x plus 2 to the power of negative 1. So the reciprocal is expressed using a negative index. Now we can differentiate this expression. Y dash equals 0 minus negative 1 outside of x plus 2 to the power of negative 2. And this can be expressed using a positive index. Y dash, our first derivative, equals 1 over the square of x plus 2. Rates of change. Gradients represent rates of change in practical situations. So for example, speed is the rate of change of distance with respect to time, such as the speed of a car, usually measured in kilometers per hour or meters per second. If you recall interpreting or drawing travel graphs, where the y-axis represents distance and the x-axis represents time, then the steeper the line, the faster the object is moving. Now there's two ways that we can calculate rates of change. We have the average rate of change, we also have the instantaneous rate of change. Now the average rate of change may be found using the gradient formula. So that's the 2-point formula. Let's have a look at an example. The distance of an object from the origin is given by the formula x equals 10t squared, where x is the distance in kilometers and t is the time in hours. Find the average speed of the object from t equals 2 to t equals 5 hours. So average speed is equal to y2 minus y1 over x2 minus x1. So that's 10 times 5 squared minus 10 times 2 squared all over 5 minus 2. And that gives us an average speed of 70 kilometers per hour. And this in fact corresponds to the gradient of the chord, so that's on the parabola x equals 10t squared, between 2,40 and 5,250. Now the instantaneous rate of change is the rate of change at one particular point. So the average rate of change needs 2 points. The instantaneous rate of change is the rate of change at one particular point, and that is found by differentiation. So let's look at the previous example. So we'll build on that. So for example, from the previous example, find the speed of the object at t equals 4 hours. So notice we only have now 1 point in time, not 2 points. So the speed is equal to dx dt, so rate of change of x with respect to time, but the instantaneous rate of change. So f dash of t, so we need f dash of t when t is equal to 4. So that's equivalent to the gradient of the tangent at t equals 4. So f dash of t is equal to 20t, f dash of 4 is equal to 20 times 4, hence f dash of 4 is equal to 80. Therefore, the speed of the object at t equals 4 hours is 80 kilometers an hour. Now, when we're asked for rates of change, if we're not told whether it's average or instantaneous, we normally assume that it's instantaneous rate of change unless told otherwise. However, if you're only given 1 point, then it's going to be instantaneous rate of change because there's no other way to work it out. You need 2 points otherwise to work out the average. The revenue of a certain company may be modelled with the function r is equal to 1/3 t cubed minus 8t squared plus 15t plus 500, where r is in thousands of dollars and t is the time in months. Part A, find the initial amount of money in the company. Now the word initial implies r of 0. In other words, the value of r when t is equal to 0. So substituting t equals 0 into the original function,
we end up with R is equal to $500,000. Part B, find the rate of revenue earned after 8 months. Now this implies the instantaneous rate of change of revenue at t equals 8 months. So we need the first derivative, so r dash of t is equal to t squared minus 16t plus 15. Substituting 8 into the gradient function, we end up with r dash of 8 is equal to negative 49. So therefore, the revenue loss, since it's a negative number, is $49,000 per month at t equals 8 months. The revenue of a certain company may be modelled with the function r equals 1/3 t cubed minus 8t squared plus 15t plus 500, where r is in thousands of dollars and t is the time in months. Find the average rate of change of revenue during the first year of operation. Now this implies finding the average rate of change from t equals 0 to t equals 12 months. So we need to use the 2-point gradient formula here. So average rate of change of revenue is equal to r of 12, so the value of the function when t equals 12 months, minus r of 0 over 12 minus 0. And this equals 104 minus 500 over 12, which equals negative 33. So therefore, the average rate of revenue loss, since this is a negative number, is $33,000 per month over the first 12 months. The revenue of a certain company may be modelled with the function r equals 1/3 t cubed minus 8t squared plus 15t plus 500, where r is in thousands of dollars and t is the time in months. Determine the points in time when there is no change of revenue. So this implies that the instantaneous rate of change of revenue is equal to 0. In other words, the first derivative, r dash of t, is equal to 0. So r dash of t is equal to t squared minus 16t plus 15, and we're going to solve the equation r dash of t equals 0. In other words, we're going to solve t squared minus 16t plus 15 equals 0. This is a quadratic equation with solutions t equals 1 and 15. Now these also happen to correspond to the stationary points of r, or the turning points. Hence, there is no change in revenue at t equals 1 month and t equals 15 months. The revenue of a certain company may be modelled with the function r is equal to 1/3 t cubed minus 8t squared plus 15t plus 500, where r is in thousands of dollars and t is the time in months. Find the points in time when the revenue is increasing and decreasing. Now, increasing revenue implies the first derivative is greater than 0. That is, t squared minus 16t plus 15 is greater than 0. You may use whichever method you like to solve this quadratic inequality. The solution here is t is between 0 and 1 or greater than 15 months, not including 1 or 15. Now, decreasing revenue implies the first derivative r dash of t is less than 0. Again, solving the quadratic inequality, we find that the revenue is decreasing for t between 1 and 15 months, not including the endpoints. Now, if you look at the graph of the function, you can see that the graph of the function decreases from t equals 1 to t equals 15 and increasing everywhere else. Determine the points on the curve y equals f of x where the curve is stationary, increasing, and decreasing. Here is the curve y equals f of x. Now, stationary points exist at x equals a and x equals b, so these 2 points here, because the gradient of the tangent to the curve at those 2 points is equal to 0. In other words, f dash of x is equal to 0. So that means that the curve is neither increasing nor decreasing at those 2 points. Now, the curve is increasing for values of x between a and b. So if you look at this section here, the gradient of the tangent at any point in this section is positive. In other words, f dash of x is greater than 0. So the curve is increasing between these two values of x. And the curve is decreasing for values of x less than a and values of x greater than b. In other words, this section here and this section here, since the gradient of the tangent at any point in those two sections is negative. In other words, less than 0.
Continuity. A curve is continuous at a point x equals a if there is no gap at x equals a. So for example, the hyperbola y equals 1 over x minus 1 has a discontinuity. In other words, it's not continuous at x equals 1 as the function is not defined for x equals 1. This is also the equation of the vertical asymptote, which splits this hyperbola graphically into two distinct sections or branches. Now, practically speaking, a graph that is not continuous cannot be drawn without lifting the pencil at least once off the page. So in this instance, the graph cannot be drawn around x equals 1 without lifting the pencil or pen off the page. Now, piecewise functions are continuous if the function values at the join are equal. So let's have a look at an example. Show that the piecewise function given by y equals x plus 6 for x less than negative 2, and we'll call that the left function, y equals x squared for x greater than or equal to negative 2 but less than 3, we'll call that the middle function, and then y equals negative 2x plus 10 for x greater than or equal to 3, and we'll call that the right function. So we're going to show that this piecewise function is continuous at x equals negative 2 and discontinuous at x equals 3. So these are our two joints, or the locations of the two joints. So for the first part, showing that the piecewise function is continuous at x equals negative 2, we need to show that the left function is equal to the middle function at x equals 2. So the left function, which is x plus 6, so if we substitute x equals negative 2 into the left function, we get negative 2 plus 6 equals 4. Substituting x equals negative 2 into the middle function, so it's x squared, we end up with negative 2 all squared, and that also equals 4. Now, left function equals middle function at x equals negative 2, so that's the join. Hence, the function is continuous at x equals negative 2. Not necessarily smooth, but continuous. It can be drawn without lifting the pencil or pen off the page. Now, for the next part, showing the function is discontinuous at x equals 3, we need to show that the middle function is not equal to the right function at x equals 3. So the middle function, that's x squared, so 3 squared is equal to 9. The right function, negative 2x plus 10, if you substitute x equals 3 into the right function, we end up with negative 2 times 3 plus 10 is equal to 4. Now the middle function is not equal to the right function at x equals 3, hence the function is discontinuous at x equals 3. Now the importance of continuity is that it is one of the conditions of differentiability, which we will talk about later.
Show that the piecewise function y equals x cubed plus 1 for x less than 2 and y equals negative x squared plus 2x plus 9 for x greater than or equal to 2 is continuous at x equals 2. So the strategy here is to show the left function is equal to the right function at the join where x equals 2. So I've labelled x cubed plus 1 as the left function and negative x squared plus 2x plus 9 as the right function. Now the value of the left function at x equals 2 is 2 cubed plus 1 equals 9. The value of the right function at x equals 2, so it's negative 2 squared plus 2 times 2 plus 9 is equal to 9. Left function is equal to right function, therefore piecewise function is continuous at x equals 2.
Differentiability. A function is differentiable at a point x equals a, provided that the function is smooth at the point x equals a for some real value of a. Now, differentiability at a point simply means that the first derivative at that point exists or can be found. A function is smooth at a point x equals a, provided that, number one, the function is continuous at x equals a, so there are no breaks or gaps, and number two, that there are no sharp corners or cusps at x equals a. Now, if a function is continuous at x equals a, that does not necessarily mean that the function is smooth. However, if a function is smooth at x equals a, or any particular point for that matter, then that does imply that the function must be continuous at that point. Now, to show that a function is smooth at a point x equals a, number one, we show that the function is continuous at x equals a. So if it's a piecewise function, you need to check the value of the function on both sides of the join. And number two, we show that the gradients of the tangents on either side of x equals a, or any particular point of interest, are equal. Let's have a look at an example. Explain why f of x equals 1 on x, g of x equals the absolute value of x, and h of x equals the cube root of x squared are not differentiable at x equals 0. I would invite you at this point, if you'd like to pause the video, you may graph these using any graphing software and have a look for yourself. Now, f of x is discontinuous at x equals 0. That's a hyperbola, there's a vertical asymptote, or the y-axis is the vertical asymptote, there's a clear break. So therefore, automatically, f of x is not continuous at x equals 0, therefore it's not differentiable. We cannot find the derivative at that point. Now, g of x, this absolute value function here, g of x is continuous, but has a sharp corner at x equals 0. So therefore, it is not differentiable at x equals 0. It's not smooth. Now, h of x is continuous, so similar to g of x, but has a cusp at x equals 0. Now, a cusp is a point that has a vertical tangent. So this is the graph of h of x. So this is the cube root of x squared. So just to show you what a cusp looks like, that's what it looks like there. So it's just at the origin there. And if you were to try and determine the gradient of the tangent at that point, it's in fact vertical. So therefore, we cannot define the gradient of the tangent at that point.
Show that the function y equals absolute value of x is not differentiable at x equals 0. First, express y equals absolute value of x as a piecewise function, y equals negative x for x less than 0, we'll call that the left function, and y equals x for x greater than or equal to 0, we'll call that the right function. Next, we test for continuity at the join x equals 0 by showing the values of the left and right functions are identical at the join x equals 0. Now, negative 0 is equal to 0, hence the function is continuous at x equals 0. Next, we test the gradient of the tangent about the join x equals 0. And we do that by finding the derivatives of the left and right functions and comparing them. Now, the derivative of the left function, y dash is equal to negative 1. The derivative of the right function, y dash is equal to 1. Now, negative 1 is not equal to 1, hence the function is not smooth at x equals 0. Therefore, y equals absolute value of x is not differentiable at x equals 0. Show that the function y equals x squared for x less than 2, y equals 4x minus 4 for x greater than or equal to 2 is differentiable at x equals 2. I'm going to refer to x squared as f of x and 4x minus 4 as g of x. First, we test for continuity at the join x equals 2 by showing that f of 2 is equal to g of 2. Now, f of 2 is equal to 4, g of 2 is equal to 4, f of 2 is equal to g of 2, therefore the function is continuous at x equals 2. Next, we test for smoothness at the join x equals 2. We differentiate f of x and g of x and show that the gradient of the tangent of f of x and g of x are equal. Now, f dash of 2 is equal to 2 times 2, therefore f dash of 2 is equal to 4, and g dash of 2 is equal to 4. Now, f dash of 2 is equal to g dash of 2, therefore the function is smooth at x equals 2, and therefore the piecewise function is differentiable at x equals 2.